Alright, so this video will cover the remainder of Chapter 6 material, starting with hurricanes. So a hurricane is the North American name for a tropical cyclone with sustained winds 74 miles per hour or greater. In other parts of the world, they're called a typhoon in Asia or simply a cyclone in Australia. But in North America, we use the Spanish-inspired word hurricane. In the northern hemisphere where we are, hurricanes rotate counterclockwise around a region of very low pressure. There are three elements of a hurricane. The eye of the storm is very, very calm. It has the lowest pressure and wind speeds. Right immediately around the eye is called the eye wall, which is where the energy is most powerful. It has the fastest winds of the entire storm system, and it has very heavy rain. So the area where you least want to get directly hit by a hurricane is actually the eye wall rather than the eye itself, because the eye wall has the strongest winds and the heaviest rain. And in the northern hemisphere, the eye wall is much stronger on the right side than it is on the left side. So that's why Hurricane Katrina just absolutely devastated that Gulf Coast area of Mississippi, because that's pretty much where the right side of that eye wall hit it head on around Biloxi, Gulfport, Bay St. Louis. Those areas just got obliterated by Hurricane Katrina. That's the most dangerous part of the storm. And around the eye and the eye wall is actually the majority of the hurricane's area in the rain bands. That's the third component of the hurricane. And the rain bands have relatively powerful wind. The further you get away from the eye wall, the weaker the winds are. And they carry these huge fronts of rain that can be miles, even hundreds of miles long. And these bands of rain will hit the land as the hurricane continues to rotate counterclockwise as it travels over the earth. So the rain bands are usually the first actual part of the hurricane that impacts an area because it extends for many, many miles outside of the eye wall. So you'll get hit with the rain bands of the hurricane many hours or even over 24 hours before the actual eye wall makes impact near you. Hurricanes have a very specific sequence of development that they follow, and not all tropical storms even come close to reaching the tropical storm stage, much less the hurricane stage. But here's the sequence. All hurricanes begin their life as a little tropical disturbance, which is basically a wave or a set of waves. And if conditions are right, the wind speed will pick up and it'll start to organize itself more in what we call a tropical depression. So a tropical depression is the second stage of life, and the third stage of life is called a tropical storm. So at this point, the storm has begun to really organize itself. It's picking up wind speed. It's starting to form a proper eye structure and an eye wall, but the winds still are not very fast at this point. So a tropical storm will usually have winds anywhere from about 40 miles per hour up towards 70 miles per hour. Now, if conditions are right, as they tend to be in the Gulf of Mexico during the summer, some tropical storms can develop further into proper hurricanes. So that means it's really concentrated its energy around a well-developed eye wall, and now its sustained wind speeds are 74 miles per hour or greater. That's what distinguishes a hurricane from a tropical storm. It has to cross that sustained wind speed threshold of 74 miles an hour to be considered a proper hurricane. So the strength of a hurricane depends upon how much water vapor condenses into liquid within the storm structure. So it's all about the exchange of latent heat. The condensation releases latent heat energy into the storm, and that creates a positive feedback loop where that continues to lower the pressure, increase the wind speed of that pressure gradient force, and it makes the hurricane even more powerful. And that's why in North America we get hit by hurricanes from around June all the way to October, November, because that's when we're near the subsolar point. The water temperature in the mid-southern Atlantic and the Gulf of Mexico is very, very hot. So it creates the perfect conditions for a hurricane to form off the coast of West Africa, travel across the Atlantic, and then hit us, because that really hot water fuels the hurricane. It creates a lot of latent heat, a lot of condensation and evaporation that fuels these storm systems. So for a hurricane to persist and strengthen itself, it must have an ample supply of very warm water, about 80 degrees Fahrenheit, 26 degrees Celsius or greater, and that water needs to be readily available to evaporate. So that's why once hurricanes actually make landfall, they immediately start to die out and lose their strength because they've been cut off from their main fuel source of that hot, readily evaporable water that they need to survive. And there also must be little to no wind shear. Wind shear will just tear a hurricane system apart. We rank hurricanes with what we call the Saffir-Simpson scale, and we base it on measured sustained wind speeds of the hurricane. So whatever the maximum sustained wind speed is, not just gusts, but it has to sustain that level for many minutes. Whatever that maximum sustained wind speed is, we use to classify the strength of the hurricane. And there are various thresholds that the wind speed has to meet to be moved up to the next level of hurricane. So there are currently 5 categories of hurricanes. So category 1 being the weakest hurricanes, barely stronger than tropical storms. And of course, category 5 hurricanes being the most devastating, strongest hurricanes that have incredibly powerful wind speeds, upwards of 155 miles per hour. So you don't need to know the thresholds for each category. Just know that the Saffir-Simpson scale is used to rank hurricanes based on their sustained wind speeds. So hurricanes are restricted to developing in tropical oceans. In the other areas of the ocean, it's just way too cold for hurricanes to develop and sustain themselves. But in the tropics and a little bit of the subtropics where we are, the water is warm enough to develop hurricanes and sustain their growth. And all hurricanes are guided by the subtropical high, because remember, hurricanes are extremely low pressure systems. So remember back to the previous unit how the pressure gradient force works. Hurricanes are always going to be forced to move a certain direction based on where the high pressure systems around them will push them. And that's kind of how meteorologists can actually accurately predict the path of the hurricane. They try and estimate where those high pressure systems are going to move, and that's going to force the hurricane to move in a certain direction with a certain speed. And so over the years, we've gotten very accurate at predicting the path of a hurricane many, many days in advance, because it's always based on where the high pressure systems around it are. Also, hurricanes cannot occur within about 5 degrees north and south of the equator because there's not a strong enough Coriolis force there to really form these. You only see hurricanes form from about 5 degrees to roughly 25 degrees north and south in both hemispheres, because that's where the conditions are right. Further north than that, the water gets too cold, and in the area immediately around the equator, there's just not enough Coriolis force to even form those initial waves in the first place. So it only forms in a very specific zone. So worldwide, hurricanes, or tropical cyclones by any name, are the main meteorological killer. And the main threat that hurricanes posed is the coastal storm surge, not actually the winds and the rain, but the coastal storm surge, which can cause a tremendous amount of flooding in coastal areas. That's actually what does most of the damage to human inhabited communities and potentially drowns a lot of people if the coastal communities are not able to be readily evacuated or their structure is not built to sustain those type of storm surges. New Orleans during Hurricane Katrina is a perfect example of this. Most of the people that Hurricane Katrina killed in New Orleans did not die from the actual wind speeds destroying their houses or anything like that. They died because the storm surge flooded many low elevation parts of New Orleans, and they just drowned because they couldn't escape. Their houses were too low, and parts of the city just flooded too quickly because the levee system broke. And this also is what kills a lot of people in Southeast Asia every year in places like India and Bangladesh that have a tremendous amount of people living very close to the coast, and they're just not able to evacuate enough people in time. And a lot of people drown from the initial storm surge that floods a tremendous amount of land very quickly. So storm surge is defined as the rise in sea level caused by strong winds and low atmospheric pressure of a hurricane. So hurricanes are strongest in the western Pacific because the water is very warm there, and hurricanes are the most deadly on average around the Indian Ocean in Southeast Asia because, like I said earlier, there's just a tremendous amount of people there that live in places that are very vulnerable to storm surge. Either they can't be evacuated easily, there's nowhere for them to go, or their buildings are just not capable of withstanding the type of storm surge that they get hit with. That's what kills most of the people. In a really bad hurricane season, hundreds of thousands of people might die from one or two hurricanes over there. There's just so many people living in very vulnerable areas to storm surge and flooding. So we've covered hurricanes now. Next, we'll move on to mid-latitude cyclones. So mid-latitude cyclones bring storms to mid-latitude regions like all of North America, essentially, all of our country, and a significant part of Canada. Mid-latitude cyclones will bring storms from fall through the spring to a mid-latitude region. Warm fronts are usually associated with nimbostratus clouds that bring steady precipitation, whereas cold fronts are usually associated with cumulonimbus clouds that bring short bursts of rainfall and potentially severe weather. So warm fronts tend to bring steady, relatively mild thunderstorms, whereas cold fronts can bring short bursts of very, very heavy, violent precipitation from the storms that they bring. And it makes sense that we generally have these cyclones in North America form from the fall through the spring. And like all other cyclones, they rotate counterclockwise in the northern hemisphere. And they have a very specific stage of development. So mid-latitude cyclones experience growth, maturation, and dissipation over about a 1 to 2 week period. These are very big, very organized, powerful systems that can sustain themselves for up to 2 weeks sometimes. So now we'll quickly define that stage of development. All mid-latitude cyclones start as a stationary front, and that stationary front transitions into a stationary wave, and then we have a full mid-latitude cyclone. And the final stage is called an occluded front. So again, the 4 stages are stationary front, stationary wave, mid-latitude cyclone, and occluded front. It's kind of a tricky thing to visualize, but page 186 of your textbook has 2 very good graphs that kind of show visually the stages of development. But the gist of it is that mid-latitude cyclones form around zones of low pressure, and all over the world they tend to flow from west to east. And because our landmass in North America is so big, we tend to get relatively severe ones relative to the rest of the world because there's a lot more space. The temperature dynamics are a lot different than other parts of the world. But these cyclonic events can last 1 to 2 weeks and bring a whole lot of storms with them as the 2 fronts kind of fight against each other and jostle for position and bring a lot of rain with them. So our final type of storm that we're going to talk about for chapter 6 is the El Nino event. And it's one of the things that we understand the least about relative to our climate. So El Nino is a periodic shift in the Earth's climate that is caused by the temporary slackening and reversing of the Pacific trade winds around the equator. It results in increased surface temperatures off the coast of Peru. We don't understand exactly why it happens. We can't predict exactly when it happens because it's a very sporadic development. It occurs randomly every 3 to 7 years on average. It's something we still don't understand a lot about. So again, the El Nino event is a periodic shift of the Earth's climate, and it occurs when the Pacific equatorial trade winds temporarily slow down and then reverse their pattern completely. And it's also associated with increased surface temperatures off the coast of South America near Peru. So these develop between March and June, and they typically reach their peak intensity from December to April. This event alters moisture and weather patterns around the world, causing drought and flooding in many regions. And again, because it occurs sporadically, it presents a challenge for governments to prepare their countries accordingly, because we can't really predict exactly when it's going to happen, and it has significant impacts on the local climate. It tends to bring fewer hurricanes to the Atlantic Ocean where we are, so it's good for us in that sense. And it also makes the southeastern U.S. more likely to be wet and cool. It changes the precipitation patterns down here. Now, what will eventually follow an El Nino event is a La Nina event, which basically creates an enhanced normal condition. So this is when atmospheric conditions go back to the way they normally are, but at a very quick pace, and it can cause some pretty drastic climate effects as a result, because it's transitioning back to its normal conditions at a much quicker pace than normal. Scientists don't know yet what triggers an El Nino event, and we can't reliably predict it for more than 6 months in advance. We can only really kind of realize it's happening after it's already started, sometimes even a year or so into an El Nino event. It's something we really don't understand that much about yet. We're trying to discover more. But for our purposes, the El Nino event is important because in our part of the world, it brings fewer hurricanes to the Atlantic Ocean, and it causes the southeastern U.S. to be wet and cool relative to normal. So our final topic for Chapter 6 is how hurricanes relate to climate change. There's a natural cyclical pattern of hurricane activity, and we believe that climate change could cause more hurricanes and stronger hurricanes, because remember, hurricanes get their fuel from warm ocean water, so it makes sense that if sea temperatures continue to rise and the water gets hotter, it could potentially fuel stronger hurricanes and also allow more of them to develop, because it'll extend the zones of the earth where hurricanes can actually form. However, so far, no such trend has been observed in frequency, so we can't definitively make that conclusion yet. However, it does seem that the most intense events are getting worse. So we don't necessarily know that more severe hurricanes are happening because of climate change yet, but it does seem that the severe hurricanes that we do get are getting worse. We've only been able to really accurately track and map hurricanes for a little over 100 years, so there's still a huge gap in our actual knowledge of hurricane events over time. There might be some very loose records of, say, Cuba got hit by a hurricane in 1780, but we can't really make any definitive measurements on how strong that hurricane was. So really only for the last 120 years or so can we accurately map the hurricanes that have hit throughout the earth. And our final note for Chapter 6 is that our longest records of climate change are provided by marine sediments. In some cases, at the very bottom of the ocean surface, some of those marine sediments have been sitting there for millions of years, and we can tell how the climate has changed over that very long period of time based on certain characteristics of those sediments. So that wraps up the material you need to know for Chapter 6. We'll continue in the next video with the material for Chapter 7.